What is up, most distinguished patrons of this channel? Today we are going to be dealing in the world of repairing cracks on thicker plates. So with that said, let's get into it. What we're dealing with today's lesson is repairing cracks. Now, this piece of scrap I drilled some holes in, and then I used a cutting torch and cut basically what we'll call cracks. But for all practical purposes, normally cracks are not straight lines, but it's what we're dealing with today. Now, this would be something that's a little bit more advanced, and you probably shouldn't be doing with a 140 amp MIG welder for a number of reasons. So that's why in this video, I am going to be covering predominantly Tig and Stick. Both of those processes tend to be very ideal for this thick a material. Now, speaking of the thickness, this plate's, I don't know, 1/2 inch to 5/8 thick, or in that ballpark, so pretty thick plate, and this is going to be some kind of a common repair you're going to find maybe on heavier equipment. Now, having success with a repair like this actually has more to do with your prep work and your understanding of how the welds penetrate, as well as your raw skill, than it is anything else. And this is one of those repairs that a lot of people simply rush, do wrong, and then the crack comes back. And my goal is to give you guys the knowledge so that that isn't a reoccurring problem for you, because nothing's worse than finishing up a job thinking you're done and then a crack comes back. So we don't want that, and that's why it's important to cover what we actually need to do for prep work on this so we don't have failures down the road. So when we're dealing with crack repairs on thicker metal, there's a lot of things you need to take into account so that you don't do a half-ass repair that's just going to fail. The number one thing probably is, do you have the skill to actually do a repair like this? And what I mean by it is simple. If you haven't done multiple pass fillet welds, or maybe a butt weld in the past where you have beveled plates and you weld it out with 3, 4, 5 layers deep, you probably shouldn't take this on. You should go and practice on spare metal that's thicker and get your skills up, because again, this isn't something to screw around with. And in the past, when I've done repairs on stuff that already has been repaired, aka cracked, at one point somebody boogered it together, and then here I am, the hired hand, to go in and fix what the previous person didn't. What I've found universally is most people go and they barely grind the crack out, and then they just weld right over the top of it. And what ends up happening, more or less, we're going to have to go turd brown here, is you barely get any penetration or fusion, and your weld just sits on top of the crack just like this. All of this is still open and not fused. Therefore, this thing gets to bending, wiggling, and it just cracks right through the weld. So universally, if it's cracked already, if you don't go and bevel it all the way out and have a full penetration weld, your success is going to be minimal at best. Now, the ideal circumstance is that you come in here and you cut a bevel on both pieces to where you're down to a knife edge or near knife edge. And again, it depends on the process. I'll talk a little bit more about each one with Stick and Tig on what you would probably want to do. But you want to come in here and hog out this material and then weld it in multiple layers deep. So you come in here and put multiple beads, you get the picture, and you're welded all the way out. If you do this properly, it's not that hard to do, and you can fully weld this out and it will be as strong in theory as it was to begin with. By cutting corners in this, your results are going to be minimal at best, like I said. Now, there's a couple ways that you can do a bevel on this plate. One way to do it would be to grind out both sides of the plate to where you have bevels on both sides and the point more or less closely meets in the center. This, if you have access to both sides of what you're welding, is probably more ideal in certain circumstances. The reason is simple. Once you put a root pass or a weld to join the two, you can alternate what side you're welding on, and that will help keep this straighter, because you got to remember, if you weld it out from this side all the way out, it's probably going to end up pulling this way. And guess what? That may be an alignment issue. Now, on something that isn't critical on, it's not going to be a big deal, but you're going to find less warping and distortion doing it this way. The downside is this simply isn't possible in a lot of repair cases because you do not have access to the backside. If that is the case, then your only option tends to be to bevel it this way and to weld it from one side out. If you have access to the backside, or if you can possibly slip a plate through the opening and more or less hold it to the backside, so something like this would be your plate, that you can slip it through there or find some way to put it, and you leave about a 1/4 inch gap between these knife edge bevels, you can weld this out into this plate, and more or less this plate will not be attached to these in any way other than where it's welded. You can leave it in place if it's like inside of a tube or something, and then you can weld it all the way out, and this will give you an extremely strong joint. The benefit in having a backing bar is pretty simple. Open root welding like here where you have a gap is actually fairly difficult to get a 100% clean weld on the back side. It takes skill. Maybe you don't have that. That's why you're in a lot better hands by running a backing strip, running hot, and trying to tie all of this together with an initial pass and then filling it out from there. If you have skill and you're used to doing open root welding, well, for one, you're probably not watching this video, but two, you can open root weld this. Like, I'm not going to show you how to do that in this video, but you could do that and it would work great. The problem with doing that is I'm not a big fan with stick welding on doing it, because generally you would use 60-10 for the open root, because 70-18 just runs and drips and you're going to have all sorts of issues. Well, normally when you're welding thick plate, you need strength from it because it's probably on some sort of equipment. Well, running 60-10 for a root pass on open root is giving you weaker weld metal at the root, and depending on how it's stressed, that metal is stressed, you may end up having cracking or failure due to that 60-10 material in at the root. 60-10 is significantly weaker than, say, 70-18, and it's also more brittle when it comes to welding stuff like this, so it's not something I particularly care to have as a root pass, which is why if I was limited to stick welding in this case, I would universally use a backing strip, do 70-18 and weld it out like structural steel. The same thing holds true with TIG. I would still use a backing strip with TIG just because that way I know I can run hot enough to tie everything together and make it all fuse, because again, any kind of lack of fusion where your weld fuses down over here, something like this where it doesn't fuse, that is just going to be a great place for a crack to form, and it cracked already, so guess what, it'll crack again. Now let's talk a little bit about bevel angles. A mistake people commonly make is they have super narrow bevels, so they would be something like this rather than the purple ones here. You do not want that even with TIG. The more narrow your bevel angle is, the higher probability you're going to have of just bridging one side to the other and leaving a whole bunch of it, all of that in there unfused. So you want a decent bevel angle on there so that, especially with sticks, so that that flux can flow out, you don't get slag entrapment, and it just works better. As far as what type of a landing to leave on it, I'll depict here where you have like an 1/8 inch landing. You would want to knife edge bevel if you have a backing strip. That way it's for sure going to melt it, so you would not leave a landing. If you're doing open root, well then you're going to want a landing based on what process you're using. If you're attempting this with short arc MIG or TIG, generally you would have knife edge. If you're doing it with stick, you're going to want somewhere between 1/16 and an 1/8 inch landing or a flat spot on that, so that you don't just blow a hole right through the bevel. So besides what I talked about here, there's another way that you can actually do this, and that is if you knife edge bevel it, have a little bit more of a bevel angle than this, and then you more or less put both of these really close to one another. So, well, if you're repairing a crack, as close as you can possibly get it, and then you put a root pass in with, say, 70-18 or TIG, and you just fill it out as much as you can with that. So you run hot and you try and burn this all together. Then you go on the back side with a grinder and you do what's called back gouging. Anytime you don't have a gap, and even with knife edge bevels at higher amperage, you're likely to get a lack of fusion where that weld is going to look something like this, okay? Well, after you fully weld this out, or at least get a couple layers of weld in this, you come back on the back side and you grind past the start of your root and clean this all up, and then you put 1 or 2 passes on this side and you bring it out past flush. I'm a big fan of doing this if you have access to the back, simply because you are assured 100% clean weld metal in this area. So before we look at this, I'm just going to give you a little bit more advice on this whole situation. This is not a job that I would trust short circuit MIG or flux core self-shielded in 035 and smaller wire. And the reason is simple. With short arc MIG, even at 200 amps, you're going to have significant lack of fusion on this thick a plate, and trying to do a short weld like this is going to have 2 huge pitfalls. One, the start of the weld is going to be cold, unbelievably cold, and will not have any fusion. So almost universally, wherever you start your weld is going to be poorly fused. And 2, it simply does not carry enough heat to really bite into the bevels. And I'll put a picture up now of a 3/8 plate I welded out in a video with a 200 amp MIG machine that had lack of fusion, and more or less what is shown in that picture is this exact situation, except this is even thicker metal. Therefore, this is a high probability of lack of fusion with the short arc MIG process, and I would not do it unless it was an absolute last ditch effort and something's better than nothing. But getting results that are going to last, I don't trust it. Now with self-shielded flux core, with your 035, like your hobby wire and stuff, the issue with that is on this thick of material with short welds, you're going to have a serious issue with porosity internal to the weld. Even if you don't see it on the surface, the weld pool more or less cools so fast that the gas that's trying to escape, that's created by the flux melting and turning to gas, will produce internal weld defects. So again, more or less, you are going to have a hell of a time welding this out with self-shielded flux core without defects. Now, dual shield, spray arc, all of that, this is perfectly fine to do with, but your home hobby wire welders, I think you're barking up the wrong tree with this. Now, with stick welding, this is definitely within the realm of stick. There's no issue with that at all. Same thing with TIG. I personally, on a repair like this, if the crack's this long, it's not super long, I would definitely use TIG for it, simply because I know 100% I can get clean metal in here, and if I did it open root, I would have a stronger open root on this than using 6010 and 7018. Now let's talk a little bit about prep here, and then I'm going to go and prep it and we'll weld this. So the main thing we want to do is create a valley, or more or less bevel angles to this. Now you can see how wide this kerf is for this cut. That's kind of a little bit of a problem. We're going to have somewhere around 3/16, maybe a little smaller of a gap. So this is definitely a situation where a backing strip would come in handy with stick, because the gap, for some of you, and based on your skill level, it all depends, might blow through more or less. But there's a couple ways that we can create a bevel. My preferred method, because I like to be fast, is to use a torch and just torch cut bevels on this. You have to be careful doing that, because if you open up the gap any more than it is, you're going to have all sorts of troubles trying to close it. So the second best way, and probably the most controllable, is to take an angle grinder with a hard rock and come in here and take your time and bevel that out nice and flat, and then go in there and weld it. Another tool you have, which if you don't have a die grinder and a burr bit, these work really good. You can get in here and more or less machine this off, and then it makes it very clean, very easy to weld. Now, another thing people commonly suggest to do on stuff like this is to drill out the end of the crack. Now, as far as drilling out thicker material like this, is it worth it? Well, if the crack is super visible, I don't think it's really going to buy you anything. However, in a lot of cases, you're not going to have this wide of a crack. You're going to have a hairline crack, and drilling it out will give you a reference point of where it actually ends, because it's pretty easy. You get to grinding a thin crack like this, and next thing you know, you can't even see where it is. And the worst case scenario is you weld through and you don't even weld it back together because you thought you were on the crack and you weren't. You were in clean material. So that's all things to consider. Well, I'm going to go and use some of the tools I have available to me and get this cleaned up. We'll take a look at it and then we'll weld it. All right, so I got these beveled out. The two on the left are more or less knife edge bevel all the way through, and I'm gonna weld one with stick, one with TIG, and then back gouge the back side and put a weld there in order to fill this out. These two are done with a lot wider of a gap, and this is gonna be done with a backing strip. Now, if you don't have access to the back side of what you're welding, it's very common to put a 1/4 inch to 3/8 opening, and then you can actually slip a plate like this with a piece of wire on it, more or less somewhere in the middle. You slip it through and then you pull it up and tack it, and then that gives you a backing strip to tie in. Now this, say it was like a big structural member or tube, would more or less just stay on the back side. You don't have to weld this plate to this, and it just gives you something to fuse to get a solid weld all the way around in here. Now, there's a couple other things I almost forgot to mention. One, when you cut and bevel this, you need to leave yourself a tapered landing. Now, I didn't do a very good job on this simply because, well, I'm in a hurry, and this has so many cracks in it. In real life, I would just toss this away. But, you know, I can't really grind into it without going into the other one. But anyways, you more or less want to start up here on the tapered ramp and then weld from clean, uncracked material down into the crack and then stop over here. Now, it's a slippery slope doing that. In the case of this, where we have a hole, welding towards a hole is going to put more heat into it, and you're more likely to blow a hole out over here, which isn't good. The problem is we don't want welding defects near this bolt hole, and with 7018 it's very common, if you're not careful, to get starting porosity. Well, if our start over here has a bunch of porosity in it, that's a very bad place to have that near a bolt hole. You're better off having it here on clean material and then welding towards it and just dealing with the excessive heat input as it gets closer. And that's really why, in the case of this, you're generally better off using a backing strip, because it allows you to weld a little bit further than you would normally be able to and tie things in better and still have meat there, to where you can use a carbide burr like this to clean up the end of the weld to where you still have a bolt hole. It just, I don't know, it works better. Now, the other thing I almost forgot to mention about this is that it's very common, if you have a crack, that crack actually, when you dig into the material, is multiple cracks, or the material's like fatigued to where it's just the further you grind in, the more stuff you see wrong, aka more cracks or holes or who knows what. And in that case, you're better off removing as much material around it as possible. And this is a great example. If I had this plate on something, say an excavator arm or whatever, and I ground it out and had this many cracks, guess what I'm doing with this piece? I'm cutting it out, throwing it in a dumpster, and welding new metal in. Something with this many cracks, especially depending on how you believe that they happened, whether it was fatigue or an impact force or whatever, is so suspect at being junk that doing this much repair, not only is it slower than just cutting this out and replacing the whole piece, but the probability of you missing something else in here that's cracked is just so high, it's just not worth dealing with. And that's why, like on heavy equipment I've repaired in the past, when it's stuff like this, you just cut it all out and replace it with new. And I know a lot of the fly-by-night guys out there, the flux core bandits, will go and just weld up every crack on this, you know, and call it good. And yeah, it may last, but I wouldn't assign my name to it. And that's just, I guess, what I'm getting at. So do your due diligence, look at it, you know, as you grind it out, make sure that you don't see more cracks. And beyond a certain point, you don't repair what you have, you cut it out and you replace. Now, with that said, I'll start out and get my TIG rig set up, and I'm going to TIG weld one of these two. So here's the root pass. I was around 80 or so amps. I didn't perfectly clean up the bevels, and I more or less got it paper thin, and you can see kind of how rough it was. The better you clean that and the straighter you can make that and less of those burrs hanging up, the better. But I basically just ran hot, pushed a ton of wires so that I knew that there'd be reinforcement on the back. Some areas it kind of blew through and I had to fill in. Other areas it didn't have as much penetration. It's kind of tricky on stuff like this because a crack is never really a straight line, and this is somewhat straight. and getting it to the same thickness start to finish is incredibly difficult, so you just kind of have to deal with it. The end result is never going to be perfect in these kind of situations. You just can't get a clean enough, consistent enough bevel, but that's all right. As long as you have some reinforcement on the back, you'll be all right. Here's a second pass, which I weaved. I tend to keep weaves well under a 1/2 inch or 12.5 mil wide. You really don't want to be doing super wide gangster weaves with TIG. Even with TIG, the metal that you deposit can become weaker due to poor grain structure. So anytime the weave was about 3/8 of an inch or maybe a little bit wider, I would end up doing a stringer and a weave. And there's nothing wrong with just doing single stringers on something like this. So like this would be 2 or 3 stringers wide. You can do that. Kind of as personal preference, I guess. For this fill pass, I just did 3 wider stringers, which, by the way, the amperage I'm running at this, I ran 80, 90 maybe on the root, and then everything else was 180 or so, and I was running pretty much full pedal. Luckily, I have a water-cooled torch here. This becomes one of those things that really sucks when you only have an air-cooled torch. It's going to get so hot that you're going to have melting issues with it. It'll start smoking on you unless you have a big air-cooled like 300 amp torch. The standard CK17 that most people run really isn't suitable for doing this kind of work. It's just too high of amperage, too high heat input. Here I did another weave to demonstrate a wider weave. And again, you don't want to go too wide with this stuff. The heat input's going to be an issue. Honestly, it tends to be more of an issue with like MIG welding or stick welding where you do those super big gangster weaves. Less with TIG simply because the metal quantity you're depositing is significantly less. But I wouldn't go any wider than this for a weave. Now, between passes, I'm not letting this cool off very much, and that's mainly to get this video done. I mean, this repair would have taken 2 to 3 times as long had I given it adequate time to cool off. But you don't want this plate to get super heated, like above 600-700 degrees consistently, because again, it leads back to that poor grain structure issue. Not to mention, if this was a higher strength steel alloy, excessive heat buildup can actually cause a change in the material itself and will reduce the strength of it significantly. So like certain tool steels, overall, just keep the heat input reasonable. Here again, I went with 3 stringers versus a weave just to show that again. When you're up at 180 to 200 amps, you can actually make a pretty wide stringer even on DC. So now I'm just going to basically flush all of this out. I'm going to get it level with the surface, and I'm going to go back and do a 3 weave cap with narrower weaves. Well, that's a wrap. It's just above the surface. There's no defects. Everything's clean. And I know for a fact that this all the way through is clean because with TIG, you generally see defects as they happen. So very confidence building when you TIG weld stuff like this because you know what's going on for the most part. Here's the back side of that, and as you can see, the reinforcement's a little bit inconsistent, and you're simply going to have that because when you run like 70 to 90 amps doing that root pass and the bevel angle is a little bit inconsistent, the thickness of the landing, the crack width, all of that is going to be an issue. So the goal really is to shove enough filler and melt the edges of the plate off good enough to where there's reinforcement. Near the hole, it tapers down a little bit, and that's because I was trying not to blow a hole or open that keyhole up any wider, but everything's above flush, so as far as I'm concerned, this is as good as it really needs to be in the real world. I did end up grinding it down and just doing a weave over it to make it flat just to show what you could do if you had access to the back, but a lot of these types of repairs you don't have access, so you can forget about doing this. I'll show you a couple quick ones on the one with the backing strip. Because the root opening was wider, I could put a wider initial pass. That was the root pass. Here's a fill pass. Overall, this welded a lot cleaner simply because that first 1-2 passes went better. And the wider gap in it, I machined more material off so it was cleaner to start with. So this is a very viable option for a lot of repairs. This is pretty easy to do. If you can run decent beads on a flat plate, you can do this type of work. So now let's talk about the stick welded one. This one was done open root. I left a pretty thick landing. I didn't go down the paper thin because my goal was to tie both sides together and not so much create a keyhole and melt through. 7018 is really not a good rod to be doing open root welding with. The puddle just doesn't work right and you can run in all sorts of issues. For this one, once I was fully welded out, I went on the backside, gouged it out with an angle grinder, and then did a 2 bead cap on it to get to fully welded out. In the real world where you don't have access to the inside, your options are going to be more limited. And that's where if you have to run a 60-10, 60-11 route to tie things together, guess what? I guess you're going to have to do that. Or you could potentially use TIG and then fill it out with stick, because you guys got to remember this stick welded one was probably a third of the amount of time to get to filled out than the TIG was. So it takes a long time to TIG weld this stuff. So TIG welding a root and then stick welding it might be a good option. So to fill it out, I tended to do a stringer pass and then a small weave to bridge the gap that was left between the side and the weld I just put down. I tend to do stringer welds mostly with 7018, except for maybe like a cap pass. I might do a wide cover pass, but on something this wide, you really don't want to try and do that in one shot. You're better off doing stringer welds like what I did here. Here's the back side of that, and you can see there isn't really any penetration, nor did I want any. I went and ground that into the metal until it was all clean, and I saw no evidence of that remaining crack, and then I welded it with 2 passes all the way out to make it clean. I didn't take any pictures of the other stick welded one, but basically it's the same as what you just saw. Just repeat over and over. I almost forgot I was running 332 or 2.4 millimeter rods at about 90-95 amps to do that. 7018s, of course. So this is the front side. These two over here were done with a backing strip. These two over here were done more or less open root. Now I was able to fill in past where the original hole would have been. That way I can take a die grinder and go in there and machine it back a little bit to get the bolt hole to where it should be. Now drilling something like this is going to put you in a world of hurt. That drill bit's just going to catch that and basically break it more than likely. So a carbide burr or something just to clean that, round it out, would do you justice. It's pretty hard to not blow out the edge on something like this. Luckily, because it's so thick, you're able to kind of run a bead down here and then across to deposit a little bit more metal and get it to where it's out there. But it takes some skill to do that, I'm not going to lie. So let's take a look at the back side, since this overall looks pretty clean and no real issues. On the back side here, I know this looks a little bit funky to have these plates welded onto here, but in the real world, if you're welding something you don't have access to the back side to, this is a great solution, and it assures us that both sides of the crack that we ground out more or less are tied together. Since we removed that 1/4 inch to maybe up to 3/8 of an inch of material on that crack, we know we're in a clean material, and by bridging everything together into this plate, we're good. This would normally get left in the real world and it would not get removed. Now, if you wanted to remove this, the easiest way is to do an angle grinder cut here and here, and then just bend it up, break it off, and then grind it down more or less to smooth it out. You could do that. Where you can really run afoul with doing stuff like this is it's very common for guys to go back and weld this whole thing to this. And my opinion is you don't generally want to do that. And the reason's simple. You are over reinforcing this particular area. If what you're welding on flexes a lot, you've more or less created a thicker material in one point. And as that beam or whatever you're welding flexes, there's a higher probability it's going to break along a weld on this rather than what you have here because you're stiffening it. So there is such a thing as over reinforcement, and this would be better off removed or left as is rather than welding it in as part of the structure. That way everything here as this flexes moves as more or less one unit and it doesn't have a less flexible spot. Well, now the moment of truth, since I did a hell of a lot of welding on this to show you guys what's going on with these types of repairs, we're going to actually cut both of these in half and inspect the welds inside and look for possible defects, discontinuities. Hopefully it comes back clean, but you never know with stuff like this. Well, I got this all cut apart and etched, and let's take a look at the results. Let's start off with the non-backing strip. This is what you want to see in your test sample if you actually go and do this, and that is 100% clean metal. There's no evidence of any defects like a lack of fusion, lack of tie-in, there's no porosity. The bevels appear to be broken down pretty decent, like you had some penetration. There's nothing on this that says, hey, we have a problem. And this right here, this repair would be 100% good to go and would be highly unlikely ever to fail again. If you were to do this on a test setup and you find defects in there, then you need to reevaluate what you did, come up with reasons why it went wrong, fix them, and try again. This isn't really that hard to achieve if you have some skill, but it's important to actually do tests like this to know if what you're doing actually works. And that's why I'm such a big proponent of testing yourself. And I say that in a lot of my videos because I don't care what settings or what techniques somebody says, whether it comes from me or some other YouTuber. Like, you can't just take it verbatim, do it, and think you're getting something. Welding in general is pretty simple, but unless you actually do a test every once in a while to know what's going on, you might as well just be taking a guess as to whether or not your technique is working. And it's not that hard to have significant defects in something like this that could massively affect the strength of it, and you'll never know if they're there unless you actually do a test like this to verify what's going on. Here's a stick weld that I did open root and then back gouged and welded to the back side, and everything looks 100% clean on this as well. Everything's penetrated, there's no lack of fusion, there's no undercut really, everything looks good. Now, we're next down in the middle. A lot of that has to do with the fact I left a pretty decent landing and then fused it together, and that area was neck down because I didn't machine that very deep into there, and because again, the intent was to back gouge and weld it out. So that's not really a defect or anything. Everything looks really good. You certainly could make the argument that there's a little bit of excessive reinforcement on it. It's probably around 1/8 of an inch or 3.2 mil or less. I mean, that's all right. TIG generally is a lot easier to make flat welds where you don't have excessive reinforcement, but for all practical purposes, everything looks good, and this is what you should be looking for in your own work. Here's the TIG with a backing plate. Everything looks good, nice and clean, just like everything else. No porosity, no undercut on the cap. It's tied into the backing strip. That little thing where it looks like a white spot on the lower right where the backing plate attaches to the main plate, that isn't really a defect. The bevel just melted back a little bit higher or a little bit further in on the second pass. So everything looks good. If you actually see like existing bevel, like a very straight line where it didn't fuse in, that would be bad. I don't see that on any of the welds that we've seen so far or this one. Using that backing strip really helps get quality welds on stuff like this and makes a lasting repair. I try to do it as much as possible. Open root welding in a repair world kind of sucks, and you're just asking to leave a lack of fusion on the backside. Here's a stick weld with a backing strip, and once again, imagine that everything is clean, no real defects, no undercut, no porosity. Now, where it tied into that plate is all nice and fused, and you can see how that second layer, I did a weave pass, or maybe a stringer, I don't remember, how it's bit in on the right side a little bit further. That's okay, you're gonna have that. I mean, the fusion with stick is going to be somewhat deeper than TIG, and your main concern is where you see those straight lines where you know it's the original bevel and nothing has melted into it. Those type of defects like you see in that picture I just put up that I showed earlier, that's really what you want to concern yourself with. An occasional bit of porosity isn't really a huge concern. It's that lack of fusion that'll make something so weak that it will break. Well, our repair today was successful, thankfully. I'm kind of surprised that there wasn't any sign of an internal defect, especially with these 7018s. I had to do a bunch of starts and stops in that vicinity. But hey, I guess, I can start a rod pretty clean and not have porosity, so I guess that came in handy. Anyways, this really goes to show that doing something like this is actually easier than you might think. It all goes back to the basics. I've stressed to so many people that I've taught how to weld how important simple basics are, like doing a fillet weld and patting the beads all the way out is basically the same type of work as doing this. And this type of repair goes back to the basics. It's proper prep, make sure it's clean, make sure that your gaps are correct, proper welding technique, which means if you can't run a bead on a flat plate, you probably won't have success with this type of a repair. And it comes down to just paying attention to what you're doing, attention to detail, and you can do a repair like this. Now, going back to short arc MIG, I know a lot of you guys are going to say, well, you can do this with short arc MIG, and my honest opinion is, hey, that's what you're paying me to give you, right? Well, this video is free anyways. But no, you should not be doing this with short arc MIG. I think even in the flat position, you are going to have one hell of a time containing lack of fusion issues on this. The only way you might be able to get away with a repair like this with a short arc MIG process is to lay the bevels back wider and then weld it vertical up to where the molten pool sinks and you're able to keep that heat and that wire, that arc, on a thin puddle, so almost directly on the metal. If you were to do that welding vertical up, I believe you could possibly do a repair like this and not risk significant lack of fusion. But I don't know, I've done a bunch of tests on this channel and off of a 200 amp MIG welder, and universally on 3/8 plate, which is thinner than this, I have not been able to reliably achieve clean welds like what you saw in this cut and etch. I've cut apart many welds and there's somewhere on it, especially near the start, that's always going to have a lack of fusion, and I don't like that. And that's why I'm telling you guys, you probably shouldn't do this type of repair with short arc MIG. Now, I know there's plenty of people online and probably you yourself or your friend that does it all the time, but I'm just being honest with you. The number one thing you can do after watching this video, if you want to make a repair like this, set up test plates, do what I did, cut it, etch it, and don't just cut it in 1 point, cut it in 3 points, etch all of them, and see what you have. If you see any defects that are significant, like a pin dot of porosity, who cares about? That's not going to make a difference. But if you have a significant lack of fusion for inches, guess what? It's no bueno. You don't want to be leaving that in what you welded and think it's going to last. It will likely crack there because, hey, it cracked in the first place and maybe it was some idiot hit something with whatever you're repairing, but hey, you have a lack of fusion in the weld, guess what's going to happen? It's going to crack again when that same idiot hits something. Anyways, I hope you guys learned something. I hope this video gave you a little bit of confidence to maybe go out and try this as a practice or do it as an actual repair. And this is something that I would classify as skills that pay the bills. This is one of those things that if you can do a really good job with this type of repair, you can make a lot of money for yourself. And not only that, you can build a reputation as a guy that can repair things that other people can't. And there's a lot of people out there that will attempt a repair like this. They don't follow like what I showed you, the attention to details, and then it fails again. You can come in and be a hero in these kinds of cases and build a reputation for yourself and a potential future. Anyways, with that said, if you got any comments, questions, thoughts on this video, feel free to leave them. Otherwise, until next time.